Hello students, welcome to fourth lecture of electrochemistry. In previous lecture we discussed about how to find the reduction potential of individual half cells. We earlier knew that you cannot find reduction potential of half cells directly, but we can find difference between two half cells. Potential difference between two half cells is equal to cell potential. That means when we connect two half cells together to create a cell, it will give us the value of difference between two half cells reduction potential, which is known as cell potential. So that means we can find the difference, but we cannot find individual values. That's why we use reference cell, so that we can give value to that reference cell and then we can compare between two different half cells, and so that you can find the value of unknown half cells. And as a reference cell we used standard hydrogen cell. Okay, as we can see here, we have H2 to H plus or H plus to H2 reaction depending on the nature of our half cell. If our half cell behaves as anode, that means it will give us oxidation reaction, and if it is cathode, then it will give us reduction reaction. And we considered reduction potential of this half cell as 0, so that now we can find the value of other half cells by joining it with this reference half cell, hydrogen reference half cell. Now next we are going to discuss about Nernst equation. Basically this equation will be used to find reduction potentials or cell potentials at non-standard conditions. As we discussed earlier, when we have unity concentrations or unity pressures of used species and normal temperature, at that point cell potential will be known as standard cell potential, or reduction potentials were known as standard reduction potentials. But what about non-standard condition? That means you don't have unity concentration. Suppose a solution used in the reaction has 0.5 molar concentration, or gases used in the reaction has more or less than 1 bar pressure. Suppose we have 2.5 bars of pressure. So at that time, what will be the value of cell potential or voltage produced during the reaction? For that we need Nernst equation. With the help of Nernst equation, we can calculate cell potentials in non-standard conditions. So as mentioned in this point, we have assumed that in previous section the concentration of all the species involved are in unity. This need not be true. That means suppose we are using different concentrations or different pressures for gases, then what? So here we have equation which gives us a reduction reaction. We have metal with N plus oxidation state, which gets N electrons and gives solid metal. The electrode potential of any concentration measured with the respect to standard hydrogen electrode can be represented by, now we have equation in which specifically these symbols used are represents a standard condition, and without that symbol, if value is mentioned, then it represents non-standard condition. That means this is the reduction potential in standard condition, where concentration of Mn plus will be 1 molar, and this represents non-standard condition. That means this concentration is not unity, except 1, it can be anything else. So equation will be non-standard, or simply reduction potential of cell is equal to standard reduction potential of that half cell minus RT upon NF into ln m upon 1 mn plus. Now what all of these values represents? So as mentioned, this represents reduction potential in non-standard condition. This value represents reduction potential in standard condition. R is a gas constant, T is the temperature, N represents transfer of electron during the reaction. As we can see in this reaction, we have N electrons. So N is equal to number of electrons. Suppose our reaction is copper 2 plus gets 2 electrons and gives copper metal. So that means N is equal to 2 for this reaction. Similarly, if you have Na plus, then N is equal to 1. And if you have Al3 plus and it gives aluminium metal, then N is equal to 3, number of electrons transferred during the reaction. Now last value, that means concentration of M divided by concentration of Mn plus. It is simply equation for equilibrium constant. As we know, equilibrium constant K is equal to concentration of product upon concentration of reactant. For this reaction, our product is our solid metal and our reactants, it is Mn plus and electron. So electron cannot be used in this case, so that means our main reactant will be Mn plus and our main product will be Ms. So solid is our product, that's why it is present on nominator, and solution is our reactant, so it will be used as denominator. Okay, so M upon Mn plus, and this F value represents Faraday, that means charge of 1 mole of electron, which will be 96,500 in round figure. Now keep in mind, we can derive this equation from thermodynamics equations, that means relation of delta G with K and relation of delta G with cell potential E. Okay, we can use these equations to come to this equation, but it is not in our syllabus and we need not to complicate our main point. It is already complicated. Okay, mathematical steps are involved in this whole topic, so it is already complicated, so we do not need to add more complicated steps in it. But for your basic knowledge, two different equations of delta G which you already learned in thermodynamics equation, which is first a relationship between delta G and E, which is delta G is equal to minus NFE, and second relationship between delta G and equilibrium constant K, which is mentioned here. Delta G is equal to minus RT ln K. So we can use these two equations together and we can say that NFE is equal to, here we can say RT ln K. Okay, so RT ln K. So this relationship is being used in that Nernst equation. That means simply if you want to find the equation for E, then what will be it? So E is equal to RT upon NF into ln K, where K is equal to concentration of product upon reactant, that means P upon R. So this equation actually represents non-standard condition. Now similarly, standard condition delta G value and non-standard condition delta G value also have their own relationship, and we already learned about it in thermodynamics equation. Putting these values in that equation, finally you will get Nernst equation mentioned in the starting point. Okay, so it is some complicated mathematical steps, not so much complicated, but still it will add some more complications in already slightly difficult topic, Nernst equation. So we are not going to discuss them separately, but keep in mind we can derive that Nernst equation mentioned in earlier point from these relationships. Now back to the point. Now we already learned about concentration of solids, that concentration of solids do not change during the reaction because concentration of solids always remains steady. So because of their steady value, as mentioned earlier in previous units in standard 11, we will consider concentration of solids as 1 or unity. So we can replace the concentration of solids with 1, or you can directly remove it. Now gas constant value is equal to 8.314 joules per Kelvin per mole. Faraday is a constant value and the exact value of F is 96,487, but we can use 96,500 for simplicity. And all the remaining values depends on the condition. That means temperature and number of electron depends on the condition, and concentration, it is already known or we can control it. So that means putting the values in this equation, you can find the value of reduction potential in non-standard condition. Okay, this equation in 3.8 is given for half cell. It is for half cell or electrode, but we can find cell potential using the same equation. Okay, here table 3.1 is mentioned, which has different values of reduction potentials, which we already discussed. Now Daniell cell, that means cell discussed earlier, copper and zinc cell, can be represented using Nernst equation separately. That means for cathodic reaction and for anodic reaction we can represent it like this. Our cathodic reaction will be reduction reaction, that means copper will be reduced. So our cathodic reaction will be Cu2 plus gives Cu metal by accepting 2 electrons. So concentration of product, it will be metallic, so we can place directly 1, and concentration of reactant, that means concentration of Cu2 plus. Now in this case we have 2 electrons transferred during the reaction, that means N value is equal to 2 as mentioned is here. So this will be Nernst equation for copper half cell. Similarly, on anode you will get oxidation reaction of zinc, that means zinc metal will be oxidized in Zn plus 2 and it will remove 2 electrons. So N value is equal to 2, so it is already placed here. But right now we are talking about reduction potentials, that means we need to use reduction reaction for zinc as well, although actually zinc gives oxidation reaction, but we will flip it later. Right now, as mentioned here, we are talking about conversion of Zn plus 2 into Zn. Okay, so that's why we use opposite reaction just like copper reaction. So zinc plus 2 will accept 2 electron and it will give us zinc metal. So zinc metal is our product, that's why unity for the metal and Zn plus 2 concentration at denominator side. So all of the values are mentioned and we have two different Nernst equations for anodes and cathodes reduction reaction. So we have reduction potential of cathode and reduction potential of anode. From these two values we can find cell potential putting them in this equation. Okay, so we have to put value of reduction potential of cathode and reduction potential of anode in this equation so that we can calculate it later. So let us put this. So you will get this wholesome equation. So reduction potential of cathode, that means copper half cell, and reduction potential of anode, that means zinc half cells. So as we can see in this equation, actually we have to put brackets over here, okay, so that this negative sign will be applicable to whole. So to remove this negative sign, and first of all we will remove some specific common things. So as we can see, what is common? RT upon 2F. It is common in both of them. Okay, so we can put it separately. Then standard reduction potentials of each will be placed separately, and then these two steps, 1 upon Cu2 plus minus 1 upon Zn2 plus. Okay, so we can put it together, but as we know these are log natural values, so minus actually indicates division, so we can place them like this. So eventually our equation will be reduced like this, because reduction potential, standard reduction potential of cathode minus standard reduction potential of anode actually represents standard cell potential. Now RT upon 2F is common for both of them, and this whole equation will be reduced as ln Zn plus 2 upon Cu2 plus. That means this also represents equilibrium constant for our full reaction. Our full reaction is Zn metal plus Cu2 plus ions will give us Zn2 plus and Cu metal. So that means we can ignore the concentration of metals because they are unity. So our main reactant will be Cu2 plus and our main product will be Zn2 plus. So product upon reactant, that means concentration of Zn plus 2 as mentioned here and concentration of Cu plus 2 as mentioned here. So this is Nernst equation for full cell reaction in non-standard condition. Okay, so this represents non-standard condition and this represents standard condition when all the values are in unity. If all the concentrations are used in unity, then it will be standard condition, which gives us standard cell potential. And we are talking about copper zinc cell, which has 1.1 volt of standard cell potential. So put 1.1 volt value here, then put the value of R 8.314, temperature it will be mentioned in the numerical 2 for this reaction because we have two electron transfer during the reaction. Faraday it will be fixed 96,487 to be exact, and 96,500 to use a round up value. Then mentioned concentration of zinc plus 2 and copper plus 2 solutions. It will give us cell potential at given concentrations. Now keep in mind, if these concentrations are in unity, that means we have 1 molar concentration of Zn plus 2 upon 1 molar concentration of Cu plus 2, that means it will become Ln1. Okay, this whole value is equal to 1, so that means Ln1. And now log natural 1, it will be 0. So if this value becomes 0, then multiplication with RT upon 2F will be 0 as well. And at that time, or at that condition, our cell potential is equal to standard cell potential. Okay, because this whole term will be 0. Now we can further reduce the complexity of this equation by using some known values or some constant values directly. We can directly place them and then we can calculate the values of them so that we can reduce the complexity of our equation. So as mentioned here, it can be seen that cell potential depends on the concentration of both Cu plus 2 and Zn plus 2 ions. It increases with increase in the concentration of Cu plus 2 ion and decreases with the concentration of Zn plus 2 ion. By converting the natural logarithm in equation 3.11 to the base 10 and the substituting the value of R, F and T, whereas T at normal temperature it will be 298 Kelvin, then our equation will be 0.059 divided by 2. So in our previous equation we have RT upon NF into Ln. Now concentration of zinc upon copper represents equilibrium constant, so let us put it as equilibrium constant. So to convert log natural into log value, we have to multiply log value with 2.303. So ln k will become 2.303 log k. Okay, so in this equation we are going to convert our ln value into log value. That's why we have to multiply it with 2.303. So let us put these values in our equation. So now we know the value of gas constant 8.314, temperature it is already mentioned 298, and F value we already know it is constant 96,487, and log natural to log value, that means we have to add 2.303. So value of 2.303 RT upon F will become 0.059, which is mentioned here. Okay, so we can directly place that value instead of mentioning this whole term. And in this specific case we have two electron transfer during the reaction. That's why this n value will be placed here, n is equal to 2. So that's why 2 is mentioned here. So now our simple equation is more simplified and it is now easier to calculate. Okay, so now we reduced it up to maximum extent. Now you have to put, all you have to put is place the standard cell potential values and the concentrations mentioned in the numerical so that you can calculate our final cell potential at non-standard conditions. Now what about the two half cell reactions which has two different type of electron numbers? In that case we should use the same number of electrons for both the electrodes, and thus for the following cell reaction example is mentioned. For a nickel half cell, as we can see, we have 2 electron transfer, but for silver half cell we have only 1 electron transfer. So if we try to find number of electrons from separate half reactions, that means reduction half cell and oxidation half cell reaction, then you will get different number of electrons. That means in this reaction you will get 2 electron transfer, for this you will get only 1. But overall cell reaction we need to balance it, to balance the electron transfer. That's why we have to use 2 Ag plus, which gives us 2 Ag solids. So that means overall 2 electron transfer will takes place. Okay, so keep in mind, in this type of situation we need to concentrate on overall cell reaction electron transfer. In previous case, that means copper and zinc case, you can directly use number of electrons used in half cells reactions, but in this type of case we have to concentrate on overall cell reaction. Now in this case, as a reactant we have solid nickel and silver solution, and as a product we have nickel solution and solid silver. Now as mentioned earlier, solid need to be cancelled out from the equation. So our main reactant will be silver having 2 moles and nickel having 1 mole. So we need to put them in this equation. So concentration of product, that means concentration of nickel, and concentration of reactant, that means we have 2 moles of silver, that means concentration of silver squared, and remaining values will be placed and you will get your final cell potential. Now, and for a general reaction, our equation will be, suppose A moles of A and B moles of B gives C moles of C and D moles of D. In that case, A and B are our reactants and C and D are our products. So equilibrium constant K is equal to C moles of C raised to C, D raised to D, that means they are our products, upon A raised to A and B raised to B. Okay, so that these values are mentioned here. Now note here, instead of K, Q value is mentioned here. That means concentration of product upon concentration of reactant, it should be equilibrium constant K. Okay, but instead of K we can see Q here. So what Q means and why K is not mentioned? So keep in mind, concentration of product upon reactant is equal to K when equilibrium is established. Suppose, understand it like this way, our reaction is A to B. A is our product, reactant, B is our product. Initial concentration of A, let us say it is 10 mole, and initial concentration of B will be 0 because reaction is yet to be started. So if we place concentration of product upon reactant at this concentration, it is not equal to K because equilibrium is not established. That means when equilibrium is not established, at that time concentration of product upon reactant will be considered as Q. Suppose at equilibrium concentration of A is equal to 5 and concentration of B is equal to 5. At that time concentration of B upon concentration of A is equal to K. At any other concentration values than this will be Q. It will be equal to Q. And when equilibrium is established, then Q is equal to K. So that means in this case we can say that equilibrium is not established. That's why instead of K, Q is placed. So now if you have any confusion regarding to the Nernst equation, feel free to ask, and we will discuss about its example later in this unit.